No, this should be the same one. There's a 3-point curve, so that's nothing new. The joke of the day for you all, normally I try to tell it before class, but it's a good one. Joke of the day is I went to go visit some dig site where they're looking for dinosaur bones, but all they could find was the lower leg bones. It was quite the shindig. That's a good one. All right, treasure that. May that sustain you through the end of this quarter. 2 more weeks, y'all, plus a day. 2 more weeks plus a day. So just to give you a frame of reference, 3 weeks from now, you're taking our exam. How exciting. So we have 2 more weeks. So today's class will probably, we're definitely going to get through this PowerPoint. Maybe we'll start the next one. I don't know. We'll see. And then next week, we'll be doing moment of inertia and torque, and a bunch of things. That may end up rolling into the week of the 14th through the 20th, which is perfectly fine because we have lots of days. We will almost guaranteed have at least 2 days for review, but we are in no rush by any means. But it may be that next week's content, even though it says it's like a week, it may roll into the one after that. So, yeah. I was like, oh, you're fine. All right, so last class I did this problem and I had a bunch of things. So my challenge to you all was make sure you kind of go through this, try to figure this one out. It's a good problem. It's got a lot of, basically it's a rotational problem that also kind of intersects with translational. So, great problem. Make sure you all can do this one if you can. You'll be in a good spot. So this is one we didn't start this one. So the angular position of a rod varies as 20t squared radians from time equals 0. The rod has 2 beads on it as shown in the figure. One at 10 centimeters from the rotation point, the other at 20 centimeters from the rotational axis. What is the instantaneous angular velocity of the rod at t equals 5 seconds? What is the angular acceleration of the rod at that same time? What is the tangential speed at t equals 5? What is the tangential acceleration? All the things. This problem is actually easier than the last one. This problem is more straightforward than the last problem was, so that's nice. All right, so what's given, y'all? We have, and once I kind of write this function, it's going to be pretty clear. May or may not be clear what we're doing here. The angular position. This is a function of the angle with respect to time. This is a function of the angle with respect to time. And, we got 2 beads on it. We have, let's just call bead 1 has a radius 1 equals 10 centimeters. That's 0.1 centimeters. The radius of the second bead is 20 centimeters. Let's call that 0.2 meters. Yeah. Good catch. And we are finding lots of things. We are solving for the angular velocity at 5 seconds. We are solving for the angular acceleration at 5 seconds. Fun fact, the angular acceleration will be the same all the time. We'll see why. So this problem didn't clarify what time for angular acceleration because it didn't matter. And you'll see why when we solve it. We are finding the tangential speed. That's tangential velocity at 5 seconds. All the things. Tangential acceleration at 5 seconds. And, one more thing, but I ran out of room. Centripetal acceleration at 5 seconds equals question mark. All right, this problem, even though it's asking for you to solve a lot of things, this one is actually much simpler. And the reason this problem exists is to remind you all if you have a function. So if you all had a function for position, so if instead this said the position is given by 20t squared, and it said find the velocity, and then later on I said find the acceleration. This is the important thing for you all to remember. This is where calculus comes in. I could not give this problem to an algebra-based course. If I give you the function for either position, or in this case angle, and you need to go down the ladder, it's a derivative. So this is where remembering the relationship between variables specifically. So how are we going to solve this problem? Pretty straightforward, actually, once you know what to do. And it's just reminding you all, if I give you a function for position, or in this case, angle, they both kind of follow that same rule. Angular velocity is the derivative of the angle with respect to time. Angular acceleration is the derivative of angular velocity with respect to time. Just like velocity is the derivative of position with respect to time. It comes from the definition of the variables. What is angular velocity? It's the rate of change of the angle. What is angular acceleration? It's the rate of change of the angular velocity. So this just comes from literally the definitions of the variables. What are they? And this is what they are. Just like velocity is the rate of change of position, angular or acceleration is the rate of change of velocity. So really straightforward. So our equation for this, I believe in your all's ability to do calculus. This is about the easiest derivative you can, well, it's not the easiest derivative you can do, but it's pretty close. Go ahead and see if you all can figure out the function that this will be. Give you all a few seconds to do that. What is the derivative of that function with respect to time? Yeah. No, you won't have to worry about partial derivatives. That's a great question. The question was, do you have to worry about partial derivatives? No. No. Good question. I think, do you all see partial derivatives in Calc 1? No. Okay, so yeah, I can't, I guess, in general, I'm not going to give you all anything that hasn't been in the class. There it is, 40t. So nice. And you know what? While we're at it, let's just do the one for angular. And you all can see that the time doesn't matter when it comes to angular acceleration. It's just 40. So no matter what time, the angular acceleration is the same. It's 40 rads per second squared. So yeah, if you want the angular acceleration at 5 seconds, really straightforward. It's 40 times 5, which is going to be 200 rads per second. So again, this problem seemed really complicated, seemed like there was a lot going on. Really simple. Now, we do need to remember that there was two beads here, and it technically says find the angular velocity for both of them. So I want y'all to spend a few seconds. I just calculated angular velocity. Which one did I calculate the angular velocity for? The answer is both of them. They have the same angular velocity. They are stuck to a rigid rod. Someone left a meter stick in here, which is great for me. If I spin this rod, you can pretend any spot on it, it's spinning at the same rate. It's spinning at the same rate. So the rate of its rotation is the same everywhere on it. It completes the same number of revolutions per second no matter where you are on that rod. Yeah?
Will we ever talk about something like that as like loose? Like if you like spin?
No, gosh, no. That's a great question. Would I ever do something like a rope that could like be bendy and stuff like that? Oh gosh, no, that's so complicated. Because like each one would have like a momentum associated with it, so that would oh my gosh, that'd be so complex. That'd be so complex to model that. That's why like modeling ropes and stuff in video games is quite complex, because you have to break it into a bunch of tiny pieces and then model what each single one does. And oh gosh, you didn't know. I've never done that problem in my physics career. So let me give you some peace of mind. That problem, you would need a computer to kind of do all those calculations.
Would that at a certain point though, like it would kind of use it?
Yeah, if you're spinning it fast enough, it does simplify to kinda. There would still actually be a bit of a delay. So, that's a great question. If you have something that's like a string, if you spin it fast enough, will it kind of be rigid? An easy way to prove that that's not always going to be true. This rod may seem rigid, but it's not exactly. And an easy way to prove that, there's a speed limit in the universe, and it's the speed of light. And so if this rod like went all the way to the moon and I swung it, that would not mean that the end of the rod would start going faster than the speed of light. The rod would actually have some bend to it then. Nothing is perfectly rigid. Nothing is perfectly rigid. It's impossible to make it perfectly rigid, meaning something that does not bend or conform in any way. Which is interesting. All right, so angular velocity, bam, done. That's for both of them. Angular acceleration, for t equals 5 seconds, there's no t anymore, so that's the answer as well. That's also for both of them. Velocity, I didn't write the equation for that, but remember, if you want to go from angular anything to tangential version of that, you just multiply by r. They will have different velocities. They will have different velocities. The one that, again, the meter stick example, now I actually have a meter stick. It hurts a lot more to get hit with the end of a meter stick. The end makes a loud noise when I hit something with it, where if I spin it the same amount, the end doesn't. And the farther away I move, the louder it gets, because it's literally going faster. The angular is the same, the tangential velocity is higher. So, important distinctions to make. And rotational stuff, y'all, is very, very, very important. Lots of things spin. Lots of things spin. So, if you want the velocity of the, let's just call it 1. Let's just call this guy 1 and this guy 2. The one that's closer. So that's going to be the angular velocity, which will be 200 times the radius, which is just going to be 0.1. You want the velocity of the other one, 200 times 0.2, which is going to be 20 meters per second, and the outside one is going to go 40 meters per second. So again, the math seemed worse than it was. You want to get acceleration, also really easy. You just multiply r times the angular. Yeah?
Are those still going to be meters per second, or would they be radians per second?
So the tangential velocity will be meters per second, the angular will be radians. So angular is the rate of change of the angle, so we have radians per second. Tangential velocity is the rate of change of distance, which will be meters per second. That's a great question.
Would tangential velocity always be meters per second?
Yep. V, and this is the beautiful thing about variables, y'all. They always have the same variables. Now, every now and then you can kind of use a couple variables for the same thing, but if you ever see meters per second, it's always velocity. I don't care what class you take moving forward. If you see meters per second, it's velocity. If you see meters per second squared, it's always acceleration. If you see joules, it's always energy. Joules can also, I guess, be work, which is the energy transferred. But that's the beautiful thing about units. They always match with the same variable. That's why they exist. Just like if someone told you, it's making certain we're all speaking the same language. Units is a part of that language. So yeah, I'm not going to do too much more here. If you want the acceleration, again, also fairly straightforward. You just take the radius and multiply it by the angular acceleration. If you want centripetal acceleration, that is just going to use the same equation that we've been using this entire time. Again, nothing fancy there. I just need to give myself room. So this problem, these function ones are actually usually, if I ever have you do these like derivative problems, they're usually actually simpler in my mind. I don't give you super complex calculus problems. Centripetal acceleration is v squared over r. You have v, you have r, easy peasy. Easy peasy. All right, so great. Kind of wraps up this section of things. So make certain you practice through these. Again, they're just like kinematics problems. Just everywhere you see, instead of it being meters, it's angle, it's radians. Instead of it being meters per second, it's radians per second. Instead of it being meters per second squared, it's radians per second squared. And just at the same time, make certain you keep rotation and linear motion separated, because they do have some nuances to them. And also remember last class. So a good question here. Well, okay, it actually tells you which way it's rotating. So this is a good practice from last time. What is the direction of the angular velocity in this problem? And what is the direction of the angular acceleration in this problem? See, I'll give you all a few seconds to figure that out. What is the direction? So this thing is spinning counterclockwise. It is spinning counterclockwise what is the direction of omega? That's angular velocity, that W looking thing. What is the direction of alpha, angular acceleration? I'll give you all a few moments to see if you can figure out that answer. So last class we did right-hand rule. So right-hand rule said if you want to find angular velocity, just curl your fingers in the direction it's going to spin. Your thumb points in the direction of angular velocity. So which way does angular velocity point? Out of the page. So omega, and I'll just go ahead and chuck this down here where I got a little bit of space. So omega is out of page. And then in the case of angular velocity or angular acceleration, we have to figure out if it's speeding up or slowing down. In our case, we have a positive angular acceleration. So we're going to say that it's lined up with a positive angular velocity. So it's going to be the same direction out of the page. Angular acceleration is the same direction as angular velocity when it's speeding up. Angular acceleration is the opposite direction of angular velocity when it's slowing down. Just like normal acceleration. So, again, just a good reminder. Directions matter. Directions matter. So, there you go. All right, let's do a clicker question. If you have a nut and bolt that's stuck and would use a long wrench or a short wrench? Most of you should know the answer to this if you've ever used a wrench. Even if I haven't taught you this. If not, take a guess. And the whole point of this question is to show you that the stuff I'm about to teach you is just giving the math to things you've experienced in your day-to-day life. That's a lot of this class. Is putting math and numbers and precise equations to things that you've experienced all the time. And this is true of anything that's stuck. Anything that's stuck that you want to get unstuck. All right, we'll go to 45 seconds. There's not, if you don't know, just guess. 5, 4, 3, 2, 1. It is the long wrench. Most of us knew that. If you didn't, that's okay. You're going to learn why today. So you're going to use the long one. It's also the same reason. Where do you push in a door to open it? You push on this, you push at a spot that's away from where it rotates. It's really hard to make a door rotate when you push near where the hinge is. Go try that with doors. So, why is this? Why is it easier to push things farther away? Conceptually, it's because you are putting that force over a longer distance. So you're having to push the thing farther, so you kind of need less force to push over that farther distance. The term, though, that we're going to be using to explain this is torque, which you all have also probably heard. Torque is a measure of the force that can cause an object to rotate about an axis. Torque is why their rotation speeds up or why their rotation slows down. Torque is the reason why things' rotation speeds up or the reason why rotation slows down. The symbol for it is tau, lowercase tau. It's a tiny little t. It's a tiny little t. So to draw this little t, you put a little curve like this, and it's a t with a little dip on the end, but a little tiny one. So more Greek, lowercase tau, T-A-U. That's how it's spelled. In English at least. The units are newtons times meters, which literally come from the equation for it. The units for it come from the equation. It is a cross product. Now, you probably haven't seen cross products, and I'm going to do my best to explain to you all where this cross product comes from, because cross products and dot products, there are two ways to multiply vectors. Cross products and dot products, there's two ways to multiply vectors. The cross product is one, the dot product is the other. How do you know which one you're working with? A cross product uses an X for a cross, and then a dot product uses a dot. Sounds silly. But two ways to multiply vectors. A cross product simplifies to RF sine theta. So a cross product, so if you have A cross B, two vectors that you're multiplying. It's the absolute value of A, or the magnitude. That's probably a better way to put it. That absolute value is the magnitude of the vector. Because remember, it's multidimensional, x, y, z components. So you find the magnitude and you multiply it by sine of theta. The dot product is A, B cosine theta. How do we find the direction of torque? We're going to do a right-hand rule thing. It'll be pretty simple. But I want to spend just a little bit of time on this whole cross product, dot product thing, because you're going to see these a lot. Yeah?
Isn't that like the counterpart of work?
Oh, is this the analogy with work?
Yeah.
There is an analogy with this, and the key to figuring out what the analogy is, so remember, every rotational thing has a translational equivalent. So degrees to distance, angular velocity to velocity, angular, etc. So that's great, because I do actually want to mention that. What is the analogy for torque when it comes to translational motion, like motion in a straight line? So the definition of torque is something that causes a rotation to speed up or slow down. Something that causes the rotation to speed up or slow down. So then let's use that same thing when it said the word rotation. What do we call the thing that if I push an object causes an object to speed up or slow down? So the acceleration is it's speeding up or slowing down. And what do you need to make something accelerate?
Force.
A force. Torque is analogous to force, which is kind of funky because it's got force in the equation. Torque for rotation is like force for linear motion. When you have a torque, my thing will rotate faster and faster, or it'll slow down. When you have a force, something moving in a line will speed up or slow down. So torque is like force, and we're going to find later on F equals ma. We're going to have an equation for torque equals I alpha. There's going to be just like a Newton's second law for rotation.
What do you mean by analogous?
Analogous, they're similar in their results. So like a force causes something to speed up or slow down, a torque causes something to speed up or slow down, but within different contexts. A force causes things to speed up or slow down in like a linear way. A torque causes things to speed up or slow down in a rotational way. Yeah.
What is the R vector?
Yeah, so the R vector, and that's what I'll need to explain cross products. The R vector is in the direction from the center of an object directly away. So from the axis of rotation, directly away from it. So R vector, that's very important because I'm going to need that to explain to you all what this cross product is doing. So that's that R vector right here. It points directly away from the axis of rotation. Okay. Cross products multiply the parts of vectors that are perpendicular. Cross products multiply the parts of vectors that are perpendicular to each other. Dot products multiply the parts of vectors that are parallel to each other. And I'm going to prove that to you all math-wise up here. Whenever you're doing a cross product, you are multiplying vectors. But you're not, what part of the vectors are you multiplying? The parts of the vectors that are exactly 90 degrees to each other. What does a dot product do? It multiplies the parts of vectors that are parallel to each other. This is going to show, you are going to see cross products and dot products all the time in your all's engineering classes. And I hope this helps you understand them, because I felt like when I was in my undergrad, I was just doing it was just math, and I had no idea what the heck a cross product was. So let's look at this cross product. It says A, B cosine theta. So I have A, and I have B, and I have some angle between them. And let's make A, a little bit bigger. It doesn't really matter. What I want to show you all is if we make A into a triangle, so if we make that A into a triangle, if you multiply, so A is the hypotenuse of that triangle. If you multiply A times sine of theta, you get this part of it. You get the part that's perpendicular to it. So if you have a triangle, let's just kind of draw it down here. Here's A, and you have some angle. This side is A sine theta. The bottom side is A cosine theta. That just comes from SOHCAHTOA. So literally what you're doing when you're doing a cross product, you're finding the part of the vector that's perpendicular to the other and multiplying it. When you're doing a dot product, you're finding the part that's parallel to it and multiplying it by it. That's all they do. There are two ways to multiply vectors. One is doing the parts that are perpendicular, one that's doing the part that's parallel. And why do you use one versus the other? Depends on your context. So in the case of rotation, let's just kind of think about what makes sense. Should we take the part that's perpendicular, the part that's parallel? So if you take the part that's parallel, let's imagine an extreme case. If I have the force vector lined up with r, so again, I got my nice little meter stick here. So this is my meter stick. The r points in the direction of the meter stick. If I pull on this meter stick, is it going to rotate at all? No. If the force is parallel to r, it doesn't rotate. What part of it, if you all want this meter stick to move the most, which way would you push? Straight down. What's direction? That's perpendicular to the radius. That's perpendicular to this rod. So the part of the force that actually makes things rotate, so if we just take this force and we draw a nice little triangle, this side is the side that makes it rotate. The side that's parallel to r does jack squat. I guess it pulls on the rod and whatever it's connected to puts some strain on there. And you hope that it doesn't rip the thing out of it. But the only part that makes it rotate is the part that's perpendicular to it. So there you go. That's where this equation comes from. It's nothing wild or crazy. It's not made up. It literally says you want to make something rotate, push it perpendicular to the arm. That's all it says. The more you push it, the stronger it is. The more the radius is, the easier it is to rotate that thing. It's easier to, again, you can try this with any door. If you push a door really far away from the hinge, it's easy to push. If you push it really close to the hinge, it's really hard to push. Ta-da! Less torque, more torque. All right. All the things, so many things in the slide. Direction of torque, really easy. So I got to turn on my, this right hand rule is not bad, but I got to turn on my webcam again for people that are online. Video capture, there we are, fantastic. So y'all can see my face twice. Well, you in class. There I am, wow, so handsome. All right, there I am. Great. So now you'll be able to see me when I'm actually describing this. So, torque. If you want the direction of torque, really straightforward. Point your fingers in the direction of R, and then you need to put your hands so you can swing your fingers towards F. Your fingers cannot swing backwards very easily, so that means it's the wrong direction. This way, I also can't swing my fingers towards F. So you put them lined up with F, and you rotate your hands so that it can go in the direction of that, and your thumb points in the direction of it. So for those online, you put your fingers in the direction of R. In this case, it's like up to the right. You then rotate your hand so I can swing it, so that you can swing your fingers towards F. Imagine like almost like a door. And you can't really, again, you can't swing your fingers backwards. Not really happening. You kind of can, but it ain't going to go smooth for you. So this problem, the torque is out of the board. And this problem, the torque is out of the board. All right, more practice. Let's try to figure out the torque in these. So, first one, see if y'all can figure out the torque of that one. Next one, see if you can figure out the torque of that one. Third one, and I'll do one at a time. So I've already done the first one. Fingers in the direction of R. And again, you kind of got to rotate your hand around. I guess one way you could do it, make it so that your palm points in the direction of the force. That kind of helps. Put your fingers in the direction of R, make it so your palm points roughly in the direction F does. Yay, my thumb points out of the page. So for this first one, torque out of page. Try the next one. And I purposely put the arrows in a spot that's going to make it more confusing. How kind of me.
Wait, is it torque and acceleration?
Yeah, we're going to find that torque is in the direction of angular acceleration. Because we're going to find that torque causes angular. Just like the net force is in the direction of regular acceleration. Yeah, the direction of torque is in the direction of angular acceleration. Just like the direction of net force is in the direction of regular acceleration. All right, so the key to this one is to make that radius vector a little bit bigger. Because as it stands, you might make a mistake. So we point our fingers in the direction of R. So that's kind of up and to the right still. I make my palm kind of point roughly in the direction F is, so I can swing my fingers all the way around. Look at that mobility. Again, if you do it the wrong way, it ain't happening. You can't put your fingers backwards. If you do it sideways, no, it doesn't happen. So you put your fingers in the direction of R and you swing them towards F. And so in this case, the torque is into the page. Makes sense because it's going to start rotating in that direction, which would be that whole counterclockwise. All right, the last one I didn't even draw R, so see if y'all can figure that one out. You're going to have to draw your own R vector. I believe in you. We're going to say it rotates from the center. That's an important clarification. Yeah.
So it's like, aren't you paying the end of the page? Or is that like left or right? Like what direction for that?
So that would mean, so if you have a torque that's into the page, that would mean that this thing would have an angular, it would accelerate, rotation-wise, it would accelerate this way. Now, does that mean it's going to rotate that way or the other way? You have to actually know which way it's going originally. If it's originally rotating clockwise, it'll get faster. If it's rotating the other wise, you're going to slow it down. So that's always an important thing to remember about acceleration and angular acceleration. They do not tell you which way something's going. They just tell you which way the velocity / angular velocity is changing. That's a great question. All right, this last one, y'all. We draw a big old R vector that goes all the way through that just to make our life a little easier. You put your fingers in the direction of R, which is down. And remember, right hand, right hand. If you do left hand, you get the exact wrong answer. You're welcome to use left hand as long as you know the answer is opposite of what you get. All right, so fingers down, you swing them towards F. We get into the page. Fingers down, swing towards F. We get a torque. Into. So great, we went over how to do this. Let's see how good of a job I did. I do not want to, whoa, spoiler alert. Yeah, we'll get to him. Oh, what? iClicker had enough of my nonsense and just crashed on me. Fun. All right, what is the direction of torque in the following image? Feel free to start thinking about it while iClicker does its best to get his feet back underneath it. You kind of got a 50-50 shot with these, to be honest. So that's nice. There's not many things in life that you got a 50-50 shot on. Most times your odds are worse. When it comes to random chance, at least. Sure, we're totally in progress. Okay. Hey, it got its feet underneath it. Look at that. Good job, iClicker. All right, so y'all have had so much time to think about this. We'll just go to 30 seconds. That's probably even overkill, but I'm just trying to account for the delay online. And let's see how good of a job I did here. Hey, I did good. Good job, me. Matt and all of you knew this already before going into class, and I did nothing and just spent a lot of time doing nothing. But you know what? I'm going to choose and believe myself. All right, 5, 4, 3, 2, 1. All right, so yeah, you draw your radius. We're going to assume that this thing's rotating about the center of its axis. I didn't specify that. This thing could be all sorts of wild, and it could be rotating about this axis, but that would be there's no way you can guess that. If I don't specify, assume it rotates through the center of it. That's a good rule of thumb. Yeah, it would. Let's see. I say it would. Maybe it wouldn't. Maybe it wouldn't. I'd have to think of all the scenarios. I think it would rotate. There is a rotation axis I could pick where it wouldn't rotate at all. So the answer could be 0. But but that'd be wild. All right, so it's down there. R is down. The 4 is you swing it and you get out of the page. So this one's really awkward to do, but thumbs are down, swing it, thumbs out of the page. Get a good stretch in there. All right, so I already mentioned this whole cross product is the perpendicular stuff. This slide just shows that. This slide just shows that in writing versus my writing. So nothing new here, but again, just trying to convey to you all what does a cross product actually do? Because you're going to do cross products. And let me give you a little sneak peek of how bad they're going to look. I say how bad. RF sine theta gives you the magnitude, but it does not tell you the direction. You want to find the direction of it? Let me just give you a little sneak peek of what a cross product's going to look like. You're going to have to set up a matrix like this, and you're going to have to put the x values of ax, ay, az, and then I say you are going to, in the future, not my class, bx, by, and bz. And when you do the cross product, so if you want the I component, you multiply this minus the multiple of that. You want this one, you do this. Yeah, it's a whole thing. So anyway, you're spared from that from this class, but when you're doing this cross product in the future, and you're like, what the heck am I doing and why am I doing this? All you're doing is multiplying the parts of the vectors that are perpendicular to each other. That's all you're doing, is multiplying the parts of the vectors that are perpendicular to each other. If you can remember that, it helps. I personally hate doing math for the sake of math. I like when the math, I understand what I'm doing and why. So hopefully that sustains you through the hard winters of Calc 2 and whatever else you take. But we'll see. All right. Why do we care? I've already mentioned this. Torque causes an object to, and this word move is not good enough, rotate, i.e. angular acceleration. And yeah, remember y'all, we already talked about a guy that figured out why things accelerate. There he is. What a guy. What a guy. Look at all the things this guy did for us. Not only describing linear motion, but also angular motion. He did so many things. This guy, again, they call him the father of physics because so many things he did are like the base level stuff that we work with. He also did stuff with light. So he did a lot of things. I don't even know all the things he did. He did a lot of things. I think he also contributed to calculus in some ways, and just like mad lad. Oh, that may totally be true.
So it was invented at the same time by a German and I think a Chinese person?
Yeah, so he did a lot. Long story short, Isaac Newton, great guy. I mean, personality-wise, I can't speak to that. But his contributions to physics were great. Like, when I say can't speak to that, don't look for any hidden meaning there. I literally have no idea if he was a great guy or not. He may have been or may not have been. I have no idea. You'll have to research that. Okay, a horizontal beam of length 3 meters and mass 2 kilograms has a mass of 1 kilogram and width 0.2 meters. Standing at this has a mass of 1 kilogram and width. That's a weird way of putting that. Has a mass of 1 kilogram and is 0.2 meters from where the beam connects to the wall. The wording there was weird, but the picture has the right idea. You got a beam. This beam has a mass to it. It is not a massless beam. That's important. You also have a mass sitting at the end of it. There it is. Oh, I see why they put that 0.2 meters. Ooh, this is a little spicy. Okay. No, the original wording was good, but I don't like it. Whatever. That's fine. We'll talk about it. Okay. What is the net torque of the system about to support the wall? There is something to solve this problem that I have not taught you yet. And it's, unfortunately, I haven't taught you center of mass. I haven't taught you center of mass, and I wish I had put it somewhere in this class, but I'm not sure where I would have put it, so but really straightforward. Center of mass is exactly what it sounds like. It's the center of something's mass. Pretty straightforward. And in this case, the center of mass is going to be fairly obvious. The reason we need to know the center of mass is because we can approximate this beam. Its mass is distributed the whole length. So we're trying to find torque. So you know what? Let's just explore why I'm even mentioning the center of mass. I'm kind of jumping to a thing that I haven't even you may be like, why? Why is he saying this? Step 2 says I need torque. Torque is R times F times sine of theta. So if we look at this equation, we know we're going to find torque. It's the only equation of giving you torque. We're definitely going to use it. We got a couple questions. What force is causing this beam? What forces are acting on this beam, causing it to want to... Why is there a torque? What forces are acting on it? Easy way to think about that, if I hold this meter stick out to the side, it wants to rotate with respect to my hand. What is actually causing it to want to rotate? It wants to rotate down. Why? Gravity. So gravity is affecting it. And then, so you say, great, the force is gravity, force is mass times gravity, awesome. You then run into the next problem. What is my radius? How far away? Where? The beam goes the whole radius, what am I going to use for radius? Yeah. There is 2 objects here. Yeah, there's 2 objects. So we're going to break this problem into 2 parts. And what I'm telling you is this beam can be approximated. We're not going to use... So what radius do we use? It's not 3 meters. That is not the radius. What we're going to use for the radius of this beam, so you can approximate this beam as if all the mass was situated right here. And the center of mass. Anything that's rotating, you can kind of approximate that it's... So where is gravity affecting? We can approximate it as its center of mass. As all the mass is located right here. And what's that radius? A nice 1.5 meters away. So this is one of our forces. This is the force of gravity on the beam. We do the same thing with the block chilling at the end. And so the width of that block matters. So this block is experiencing a force due to gravity. Now notice where I put this arrow, dead center. So that is the force of gravity on the, do they call it anything? We're just going to call it a block because it looks like a block. I want you all, so in my givens, we're going to say the radius of the beam, as weird as this seems, but remember I told you it's where the center mass is 1.5 meters. The mass of the beam is 2 kilograms. The mass of the block is 2 kilograms. Nope, 1 kilogram. It didn't say it in the problem. 1 kilogram. I want you all to see if you can figure out the distance for that block. Based on where I drew that arrow and knowing that that block is a width of 0.2 meters, what is the distance from my pivot point to the center of mass of that block? What is the distance from the pivot point to the center of that block? So the center of the block is going to be at 0.1 meters. You know, half of 0.2 is 0.1. So what is the radius? How far away is that block? 3 minus 0.1. 2.9 meters. Because the center of that block is not sitting at the very dead end of that beam. It's slightly, and you can see that in my picture, y'all. There's a very tiny little shift there. That little tiny shift. So this little tiny shift right here is 0.1. That's to get that center mass. Okay. At this point, the math is pretty straightforward. It's RF sine theta. The radius vector is perpendicular to the force, so it's not going to be bad. I will set it up for you all. Both of these are being pushed the same direction. That matters. If the torques are in these are vectors, y'all. If torque is one way, if the force of one of these was up instead, I'd have to subtract them. So the net torque. So the torque is going to be torque 1 plus torque 2. Just like when y'all remember free body diagrams, y'all, net force, and you had to add up the forces. A force that's up and a force that's down had to get subtracted. You have to be careful of that with torque as well. Yeah, and at this point, fairly straightforward. So torque is going to be R beam times mass beam plus R block plus mass plus multiplied by mass block. In this problem, the angle is 90 degrees, you get the max torque. That is why it is the hardest to hold something exactly parallel, like your arm, holding it directly to the side of you is the hardest because you're getting the maximum torque due to gravity. The more up you hold it, the more your shoulder can kind of take some of that burden. The more down you hold it, same thing. So again, it also connects to stuff you all have experienced. It is the hardest to hold your arm straight out because the force of gravity is exactly perpendicular to the radius vector, i.e. max torque. Yeah.
Is the, 9.8 anywhere?
Oh yeah, that was silly of me. Thank you. The force of gravity is not just M. That was silly me. M times G. Ugh, thank you. I almost misinformed you all. There we go. Yeah, gotta chuck a G in there. That matters. That matters a lot. If you don't have gravity, you don't have a force. So yeah, at this point, you just kind of plug it in and you get an answer. We got a couple minutes, so I'll just chuck it in the calculator real quick. Block. I just didn't write the word block. Radius of block, mass of block. So let's kind of write it out with numbers. The more you write out, the less likely you are to make a mistake. That rule will carry through the rest of your all's college career. The more you write out, the less your brain has to work, the less likely your brain's going to make a mistake. That's why giant whiteboards are awesome, because they give you so much room to write things out. Okay, well that's just going to be highlighted now. Plus 2.9 times 1 times 9.8. Not ideal that it's kind of skating its way down there. So torque equals all of that plugged in a calculator, which definitely you need a calculator for. If you can do that in your head, you're a better mathematician than me. You could probably approximate it. 57.82. And if you ever like, man, what are the units for torque? Just think of what you all did. You multiplied force times distance. F times radius. The units for torque literally come from the math. Newtons times meters. I do not have the units for torque memorized. I just know they come from the math. It's like the units for momentum. All right, y'all, we did it. Yay, torque. Next week, y'all, the difficulty we're going to start talking about moment of inertia, and it's going to be something else. Moment of inertia is its own little fun thing. But it'll be great. We'll learn about it. It'll be wonderful. Have so much fun. And yeah, we'll keep on rotating, y'all. All the rotation. That's literally just what we're ending the year with, is things rotating. And how does that work? Have a great weekend, y'all. I'll see you on the other side.